Today's lesson will be about transformations of functions. This is section 1.7 in your textbook. The essential question for this lesson is, how do you use transformations to sketch graphs of functions? In the previous section, we talked about parent functions. Well, in this section, we're going to learn that many functions have graphs that are transformations of parent functions. So for example, let's say I wanted to know what the graph was of a function h of x, which was equal to x squared plus 2. I might recognize the fact that we had a parent function, f of x equal to x squared. So if I look back at my original h of x, I would realize that h of x is simply equal to f of x plus 2. So if I would take the graph of f of x and shift it up 2 units, I would get the graph of h of x. So here we would have the graph for f of x equals x squared. Now, if we were to move this 2 units up, we would have a graph that looks something like this, that comes down, goes through here, and then goes back up, where this distance here is 2 units, okay? So h of x would simply be the original graph shifted up by 2 units. So let's look at another example. Let's say I have g of x is equal to x minus 2 quantity squared. This would be related to the parent function f of x equals x squared by shifting the graph to the right 2 units. So our original function g of x is simply equal to f of x minus 2. So now let's summarize vertical and horizontal shifts. A vertical shift of c units up is simply going to involve taking the function and adding c to it. So h of x is simply equal to f of x plus c. A vertical shift of c units down is simply you take the original function f of x and subtract c from it, or h of x is equal to f of x minus c. A horizontal shift of c units to the right is simply going to say you're taking the original function, and instead of having f of x, you're going to have f of x minus c. So h of x is going to equal f of x minus c. And lastly, a horizontal shift of c units to the left is simply going to take the original function f. Instead of having f of x, you're going to have f of x plus c. So in that case, h of x would simply equal f of x plus c. Another common type of transformation is a reflection, okay? Now, if you consider the x-axis to be a mirror, then the graph of h of x is equal to minus x squared would be the mirror image or reflection of the graph of f of x equals x squared, okay? So just think of the axis as being a mirror, or you could think of it as flipping the graph around that axis. So if we're talking reflection in the x-axis, the new function is simply the negative of the original function. So h of x is equal to minus f of x. And similarly, reflection in the y-axis would simply be the new function h of x would be equal to f of minus x. You'd plug in minus x for x in the original function, and you'd get the reflected function h of x. Now, everything we've talked about so far have been rigid transformations, such as horizontal shifts, vertical shifts, reflections. These are all considered rigid transformations because the basic shape of the graph does not change, only the position. Now we're going to discuss non-rigid transformations. Now, these are those that cause a distortion or a change in the shape of the original graph. Now, the first of these non-rigid transformations that we will talk about is vertical stretch. If you can think of the graph being written on a piece of rubber and you would stretch it vertically, okay, pulling on it, that would be vertical stretch. Now, one of the things we might do is to represent this using functional notation. So if we were to use functional notation, vertical stretch would look something like this. So vertical stretch would be represented by g of x is equal to c times f of x, where c is greater than 1. So long as c is greater than 1, then if you multiply that c times an f of x, you're going to stretch whatever f of x was originally. Now, the opposite of vertical stretch is vertical shrink. Okay, now this can be represented by the same exact way vertical stretch would be represented, but now c is not greater than 1. C would be between 0 and 1. So another way of looking at it is, if c is a fraction, then c times f of x would result in vertical shrink. So obviously, if we have vertical stretch and vertical shrink, we are also going to have horizontal stretch and horizontal shrink. So this would be represented by h of x is equal to f of c times x, where c is greater than 1. So if we take whatever x is and we multiply it by a number greater than 1 and plug it in the function, we'll get h of x, and this will be horizontal shrink. Now, horizontal stretch, on the other hand, would occur using the same setup, but now c, instead of being greater than 1, would be between 0 and 1. So if c is a fraction, f of that fractional number times x, you'd plug in a fraction times x in place of x, you would get horizontal stretch. Now I would like you to match the rigid transformation of y equals f of x with the correct representation of the graph of h, where c is greater than 0. So in other words, match up a, b, c, and d with 1, 2, 3, and 4. Post your answer in the drop box.